Thank you. Good evening, folks. My name is Harold. I come from France. And like many other French people, I come from France. Are there other French people in the room tonight? Who wrote that horrible script, actually? Oh, yeah, it was me. Are there other French people in the room tonight? No? What a shame. Okay, so I grew up in France, and like every other French future mathematically interested people, at this time I was very much interested by... No. No way, no, not math. Who said frog legs? No. I was very much interested into music. I played the violin, and that was my big passion. So it was much later, age 16, that I got interested into math. And nowadays, when I say, oh, actually I'm a researcher in applied math, but I also play the violin, people ask me, sorry, so what is your job? Also, sometimes people say, oh yeah, there are lots of connections between math and music. Really? That has always surprised me. So I wanted to do my little research to find out, and here's what I found. So apparently, many people believe that the mathematical skill and the musical skill are related. In other words, if you are good at math, you will be good at music, and vice versa. And sometimes it's called the Mozart effect, according to which if you would make small children listen to classical music, they would become good at math. All right? Well, apparently it doesn't work like this, because there is very little support for any of these propositions. And it would be actually very difficult to prove or to disprove these hypotheses. And if I had to choose a statement, I would just say, like the mathematician Tim Gowers from Cambridge, that basically your ability at doing math is related to your ability at doing music, just the same way as your ability at playing football is related to your ability at playing cricket. Okay? Well, there are some exceptions. So the first one is that apparently it was found that if you use music to teach children how to compute fractions, it works better, okay? Don't generalize. I have only found that example. Might be other ones, but... And there is another example which comes from, it's a quote from a very famous physicist. Albert Einstein said once, was it Homer Simpson? I don't remember. So he said that the theory of relativity came to him via intuition, and that music was the driving force of that intuition. I didn't know what to do with that. Maybe I'm no Albert Einstein, you know. Yeah, so that was it for this part. But actually, if I had to fight for a connection between math and music, I would choose to present the physics, because the physics of sound have been studied since many, many years. Oh, now I see I'm starting to bore you, yeah? There was a few interesting figures. So the first one is Vincenzo Galilei. So he was a music theorist from the Italian Renaissance. And he was also the father of Galileo Galilei, who later became known as the father of modern science. So in other words, Vincenzo was the grandfather of modern science. And there is another guy called Marin Mersenne from France, who, wait, that's an important detail, yeah. So he is known as being the father of acoustics. So quick remark here, father of science, father of acoustics, who the hell is the mother? So if you know the answer, I would be happy to get some advice on that. I don't know how we do that. So since then, acoustics has developed a lot, and now it's a field where Basically, we deal with a lot of subjects from various problems in engineering and in real life, yeah. And yeah, I will introduce you to some of the basics of acoustics. But before I do that, let me ask you a little question. So who of you play a musical instrument? Okay, can I ask you what you play? Oh, that's not my favorite. So what I want to show you is that actually you could have all raised your hand and say, yeah, I play a musical instrument, because we all speak, we all make noise with our fingers, we can all whistle. So the physics of our body is the same as the physics of a musical instrument. And that can even be carried over to more general things, because there is basically sound everywhere, literally. And here you might think, is this fella really sound? Sure, look it, I will explain. So let's look at a musical instrument out of, let's say, randomness. Let's pick the violin, okay? So there are typically, the principle how it works is very simple, all right? So there are two things. There is the exciter and the resonator. So the exciter is the one that initiates the sound, and the resonator is the one that amplifies or sustains the sound. So for the violin, the musician will use the bow to excite the string, which will resonate, all right? So that's very simple. Easy, isn't it? Okay, so let's see if you have understood that part. Everyone take a sheet of paper. No. But before I go on, let me have a drink. Well, now you are thinking, that's not how you drink, all right? And I know that very well. Let's see if it works. Okay, so here, the exciter is my wet finger and the resonator is the glass, okay? So here, in this case, the exciter is the stream of air that comes out of my mouth, and the resonator is the air contained inside the bottle. Okay? Well, that's pretty much it. So this demonstration shows that the physics of musical instruments apply to many other objects around us. And that's what I have done since I started studying science. As I started to get interested into musical instruments, then I did my PhD on rocks physics. And now I'm working on the motion of the brain for people who are suffering of traumatic brain injury. So yes, they literally sound everywhere.